Hi everyone, this is Abhishek Verma from Synopsys India Verification Group, and today I'm here to talk about extending UVM methodology for verifying mixed signal components. In the last presentation, TVS was talking about some kind of checks and functional models for analog components in the SoC. Now this is something which might click after what we have discussed already, is that we are talking about coming up with a test bench with a similar look and feel of a digital test bench, and especially based out of a methodology which is being widely accepted to be able to verify mixed signal components as well. So as we go down the slides, the picture will be clearer, but that would be the basic agenda of my talk today. Moving on to the next slide, this is just a legal reminder I've been asked to put that all the information content in this presentation reflects Synopsys plans as of date of this presentation. Such plans are subject to completion and are subject to change, and it's all copyright protected by Synopsys. Thereby leading us to the agenda for today. I'll be talking about the target audience and the application for UVM-AMS. Then what do I actually mean by AMS Testbench Technology, and what is the key features or functionalities which I'm being borrowing from the digital test bench and trying to use them in the AMS world. Then go and look at the overview of the UVM-AMS test bench, and again this is specific to UVM, but again can be extended to any methodology of choice, followed by which we'll go and look at the look and feel of the test bench. So there is a small example which tries to show what kind of verification we are trying to achieve by it. And then followed by that, there will be a set of features which are being demonstrated, such as how can you write assertions on system of system Verilog type, but be able to verify mixed signal content. Then we'll talk about some of the checkers which are again part of the application package and help in various kinds of checks that are deployed for AMS verification, or rather components with mixed signal, SoCs with mixed signal in it would deploy these kind of checkers to check, say, the tolerance on a supply line and stuff like that. Finally, we'll also look at the use model. So what is the proposed use model with this kind of a test bench? The built-in generators and how the existing generators can be extended to generate any kind of stimulus on a or pin wiggling bus functional models for any node of the electrical world. Finally, I'll try to conclude by talking about the benefits and the future work which will go into this kind of a test bench methodology. Moving on, the target audience and the applications would be SoC integrator which has analog IP developers, and the domains can be anywhere from automotive, communication, multimedia, PHY, low power, and IP. So again, analog components are becoming more and more complicated, and they are becoming part of almost every SoC in any domain. So pretty much everyone gets affected by it. And what kind of applications do we target by such a methodology? So it's mostly about verifying components like ADCs, DACs, amplifiers, comparators, PLLs, low power controllers, voltage reference, PHYs, again any custom IP. Basically the idea is any time-based discrete verification component. So any component which works on time-based discrete sampling can be verified by using this kind of a test bench methodology. Okay, that brings us to what we mean by AMS Testbench Technology. Again, having a test bench for AMS components, so if you look at the diagram below, on the left hand side is the box or the test bench which has completely digital components in it, and we have a very set and defined methodologies and language constructs to be able to do verification. Something like a coverage driven verification or a constraint-random verification is a common thing for digital world. And the idea of this kind of a test bench, or the UVM-AMS AMS Testbench is to have a test bench which has a similar look and feel of a UVM test bench and be able to deploy it with analog components in your DUT. So that's what pretty much the idea is on the right side, that you can see now some of the analog components also being part of it. Right. So technology for mixed signal SOC verification should be able to leverage constraint-random verification and advanced HVLs like system verilog. The idea of this package is to have the methodology enhanced with new constructs for analog block and be able to provide AMS coverage in system verilog test bench environment. So that is the primary area of focus of this particular test bench technology, is to be able to have constraint random verification in system verilog be deployed to AMS test benches and be able to provide some kind of a functional coverage on the AMS side as well. So having these ideas in mind, move on to the next slide. And this slide gives the idea of how or what is the basis of such a test bench. Now, on my right-hand side is a diagram, right-hand side corner, which talks about the integration of SPICE or Verilog AMS model into system Verilog. Now, that's the key here. That's the real to electrical conversion, and the electrical to real conversion back helps the test bench be able to drive and sample the SPICE or Verilog AMS nodes. So that is something which is, again, abstracted from the user. This is a layer which is built in with the tool itself of VCS for us. It provides a layer between the SPICE-based components and the system Verilog to be able to interact seamlessly, right? And that is done by this layer of real to electrical and electrical to real node conversions. Now, as you can understand, SPICE has electrical nodes and system Verilog has real variables. Now, if we are able to map these two, then most of the functionality of being able to drive a node for driving purposes and be able to sample a node for monitoring or coverage purposes can be achieved very easily. So that is the first and the basic usage of this test bench, to be able to have an environment with SPICE components and system Verilog test bench sitting together to be able to talk to each other via the electrical to real conversion and vice versa. The second important point of the basic usage is the asynchronous analog event. So then again, VCS with some of its API provides, then again if you move on to the right side block, it talks about the DUT and the test bench are instantiated and connected using SV interface. So if you look at the instantiation of the DUT, the A to D converter DUT, it's a SPICE block, and then we are able to pass the real variables to it, right, where the electrical nodes are supposed to be passed, and that is automatically the electrical to real and real to electrical models are inserted automatically by VCS. So that's another idea. So if you look at it, the test bench top also looks pretty much like a digital test bench where the analog component is instantiated or the SPICE component is instantiated as is, and then the test bench is also, which is system Verilog, is there, right? And then the interface is used to bind the two together. Again, one point of a point to remember would be the fact that the analog component or the SPICE DUT which has been instantiated over here definitely calls for a co-simulation. So if not just the digital simulation, you would also need a co-simulation, say SSIM or NanoSIM for that matter, to be able to, or VCS extended solution for mixed signal, VCS XA, to be able to do the SPICE simulation part of it. But the idea is the look and feel of the test bench or the overall test bench will still look like a system Verilog test bench. And then finally, towards again the left hand side, you can see that the program block or the driver instance, which is trying to drive that particular real signal inside the interface, is actually able to drive a particular voltage on that real variable, and then that real variable will actually pass it down as electrical value to the actual SPICE DUT. So the bottom line is we have something now available to be able to drive and sample SPICE DUTs from system Verilog. Moving on to the next slide, and once we have understood the fact that there is a possibility of having that which is in SPICE being driven and sampled from system Verilog, then we move on to see some of those advanced features which I can do and write on top of this kind of a layer. So one of which is assertions, and again these assertions come very handy when you're trying to put some kind of self-testing in your test benches. So again, here is an example of synchronous and asynchronous immediate assertions. And in case of synchronous, we check the assertion on passage of every clock. If you can see on the left-hand side top corner, there is an assertion for a particular analog node that's called top.vref.analog node, and the assertion is to check that the node should never cross a voltage of 1.8 volts, right, at passage of every clock. So this assertion will be checked synchronously at every clock, and once this node is less than equal to 1.8, that's fine. It just exceeds that value, there is a $ error or an error display on the console saying that the node has reached value which is greater than VDD, and it is not supposed to do that, right? So again, bottom line, the idea is you can now use these analog nodes as simple real variables and be able to write assertions on it, right? On the next side is something for the asynchronous assertion of signal. So here in this case is where I was also talking about in one of those slides previously, where you have the capability built in with VCS and be able to capture voltage values at particular electrical node. So then you use Synopsys PLIs to be able to get the voltage at that particular point at any point, and then write something like a always at. So basically those are asynchronous events, and once that particular node crosses say for example in this case a voltage of 1.8, the whole PLI unblocks and then it goes and checks for the assertion. So the bottom line is not only you can write synchronous assertions or be able to drive and sample on clocks or a digital signal, you also have the capability of waiting and counting on an asynchronous event from the electrical world or the SPICE world itself, right? So that is the basic idea being demonstrated in this slide. Moving on to the next slide. Again, these are some of those features which I've been talking about. So this talks about all the different kinds of checkers which are built in this UVM-AMS package, or SVMS package as we say, because again this can be extended to any methodology, VMM or UVM per se. So some of these checkers are very interesting and they help save a lot of time. All you need to do is instantiate the checker on that particular node and provide the the required arguments with them. So if I talk about something like a threshold checker, it checks that the analog signal remains within a given high and low threshold, right? And then again you can perform this check synchronously or asynchronously depending upon your choice of logic. So the idea is, as you can see on the right side, there is a signal, and if it is in range of that particular high and low value, this checker doesn't fire, and then if it crosses any of these two limits, the checker fires an error or a warning message depending upon the kind of verbosity you have or severity you have set for the same, right? Now you can also have a lot of flexibility with these checkers in the sense that you might want to switch them off at a later point in time. Say for example when the PLL is locking, your threshold checker would be doing some kind of a threshold check, and then when the PLL has locked, then the threshold checker should have different lower and higher limits. So all those kind of changing the configuration of these checkers on the fly, stopping them, starting them again, all those kind of things can be very easily achieved by the basic ideas of any methodology driven components. Similarly, you have more checkers like stability checker, so that checks for an analog signal to remain below or above a given threshold. So you can provide a V reference and a tolerance. So V reference plus minus the tolerance, the checker will not fire, otherwise it will fire an error or a warning message. Then you have slew checker, so that checks for the analog signal rise and fall with a given slew rate plus minus a tolerance, and similarly a frequency checker where it will go ahead and check the analog signal frequency is within a given tolerance. So there are a lot of these kind of checkers built in the package. All that needs to be done is to be instantiated and connected to the correct node. Again, moving on to from some of the basic features to the primary use model of this kind of a test bench, and the kind of example which we would want to explore and showcase this methodology would be something as shown in slide number 10 here. So if you look at the DUT now, it has some of these analog and digital components, and what you can see is all the other components around it, some of them being digital, have their own set of drivers and self-check and test case, but the idea is now the analog component is not providing any handicap in doing that for those components as well. So you can have analog components in your DUT and still be able to drive any kind of signal on that particular node and be able to capture the output, monitor it, and use them for coverage purposes, right? Again, these kind of components are fairly subjective to be discussed in this scope of this presentation, but something like a self-checking and coverage can be very easily developed once you have an interface or once you have the analog component talking to your system Verilog components, right? So again, as you can see, this is a very typical test bench of digital world, and the idea is to bring it to analog world and be able to leverage from what digital methodologies provide, such as constraint-random verification, functional coverage, etc., and be able to deploy them to touch with analog components as well. Finally, moving on to the slide number 11, and this gives a typical IP verification environment. I mean, again, it's very typical of a digital test bench, but here the idea is that the DUT is an analog IP, and now it provides a little bit more details of how these components are interacting. So on the side, on the left side, where you're trying to drive the DUT, these are all UVM-AMS voltage components. So now these are basically generators and drivers of the particular electrical or real signal. And then there is a transaction layer which is called this UVM-AMS real, and this class or this base transaction class is responsible for modeling the real numbers which can be used to drive and sample. Now, as you can understand from the digital world, that you cannot write coverages on real numbers for now. So in that case, what this class provides is a way of mapping these real numbers into integers by a measure of accuracy, and then be able to write coverages on those integers, integer numbers, or write constraints on those integer numbers, right? So that's one of the basic ideas where this transaction layer of UVM-AMS real fits in, and is very handy to be able to drive and sample any DUT which is analog in nature. Right. So once you have your base transaction available, that's the bloodline of the entire test bench, and each of these drivers, the generators, the coverage collector, the checkers, and the monitors, they talk in that language, and they talk in terms of UVM-AMS real, and then they talk to each other with that particular object and be able to provide various capabilities of either coverage or say self-check or say able to drive a node with a random value. Now a typical example of that here which I can take is say an ADC, and now I can write constraints to say drive the node or the V in with a value from say 0 to just 1 volt, given that the plus minus VDD is 0 to say minus 1.8 to 1.8 volts is the minus VDD to plus VDD for this particular ADC. But I want to see a test where I want to constrain the V in from 1 to say 0 volts to 1 volt, and then observe the output, right, and then convert them to integers and see if exactly there is a self check or the exact voltage is matching with respect to what, or the exact value of the ADC output is matching with respect to the value which V in is supposed to bring in, right? So that's a very simple example I have taken to demonstrate the purpose. So again, finally moving on to the driving part, or the generators, and this is something which I wanted to talk about a little more, so that's why I put a separate slide for this. So here the idea is the test, and again as I explained in the slide earlier, the test will be able to constrain the input voltage for a particular node, right? And this topology supports SVTop, VAMS/spice leaf. So if you can see, the testbench side of it is system Verilog, while the DUT is either a spice DUT or the self check is, say, a Verilog AMS based reference model, right? So again, this is very very useful and very helpful environment to be developed and be able to drive and sample from SV or UVM based kind of a test bench, right? And as we talked about it earlier, the insertion of A to D and A to A, that is the real to electrical and electrical to real, happens automatically by the tool. And then this is constrainable SV real to drive analog nodes. So as I talked about it a little bit earlier, and I would like to reiterate over here, is that the transaction layer of SV real or SV-AMS real tries to model a system where you can put constraints on real number, right? Which actually, mapping them to integers and then put constraints on it, and then be able to drive that value onto the particular node of the electrical device or the DUT here, or the spice DUT here, right? And then all these are basically, if you look at these components which are supposed to drive them, they're all extended from a base class library of UVM-AMS or SV-AMS, and that's why they are called SV voltage components or SV-AMS voltage components. And again, depending upon choice of methodology, these components align to that particular methodology. So again, it can work in both both methodology, as in UVM or VMM, but right now the scope is for UVM, right? So if you look at the generic, that was a generic description of how a voltage generator would look like, but the library or the application package of UVM-AMS do provide for certain set of generators automatically built inside the package, one of which has been shown over here as a sine voltage generator. Now as you can see over here, this is a very typical UVM environment where the environment extends from UVM component. It goes ahead and instantiates a sine voltage generator, which is library, provides the Vmin and the Vmax as 1 volt, plus minus 1 volt, and then the frequency as 1 megahertz, right? And then during the build phase, it goes ahead and creates that particular generator, right? So as you can see, all the methodologies specific stuff are aligned, and then here it will start automatically run throughout in the run phase, right? So this is again a component. The generator is again a component which is extended from UVM component, but now it's capable of generating these real values which will look like a sine wave. Now similarly, we have capabilities of generating square waves, sawtooth wave. Then you can do a lot of mix and match. You can add two waveforms on top of each other to, say, have sine plus noise simulation, or you can have a lot of those modulated kind of waveforms where you can have say amplitude shift keying kind of waveforms done. But again, that's very subjective to a particular test bench. And finally, trying to conclude with what been discussing for the last 30 minutes is to have the test bench methodology for AMS, or to have a clear methodology for mixed AMS SOC verification to enable consistent digital and analog verification. So the idea is in the existing digital test bench environment, be able to do something for the analog components as well. Tight integration between VCS and custom sim. This is something for us to be able to integrate the VCS with the custom simulation for the analog components. Cover holes in mixed AMS block level verification, so synchronous and analog asynchronous verification, usage of ref model for self-check-in and crooked simulation. again, this has to be traded off with performance, and because when it comes to SPICE, you definitely need to trade it off with performance of the simulation versus the quality of the simulation. And finally, to build or come up, and this is a more ambitious idea, to come up with an ecosystem which has all the different various benefits of digital environments, such as verification planning, regressions, coverage convergence, and self-checking. And partly it is achieved by the fact that we have already brought the capabilities to UVM, and whatever latest can be done in a methodology, SV-based methodology, can still be done here. But specific to AMS, we need to still go ahead and build a complete, robust ecosystem with verification planning, regressions, coverage convergence, and self-checking in our minds, right? So that's pretty much it for today, and that brings me to the end of the presentation. Now I guess I'll take the question and answers. Thank you.
Thank you, Abhishek. Francois, do we have any questions from Grenoble? Okay, it doesn't appear that we have any questions from Grenoble. We have one question online for Abhishek. Is this product released?
That's a good question. So this is not part of the VCS, the latest VCS which has gone out, which is, I guess, 1209. But if you want this product, then you need to contact your local Synopsys person, and this package is a different product altogether. So it is not released as such, but it can be made available to customers on request. Does that make sense?
Yeah, there's another question. This is Mike Bartley from TVS in Bristol. There's another question. Hi, this is Mike Bartley from TVS in Bristol. Some more questions online.
Hi, Mike.
Hi, just one from Sam Pascal. Any reuse of the UPF types of power intent from digital domain in UVM-AMS Testbench flow?
Right now, there's nothing like that, but yeah, that is also work in progress, is what I can say. So there's something that is something on the low power side. So there are discussions going on with UVM low power integration into this, but that is interesting. And again, we can engage with someone who is already doing something, and then be able to collaborate and come up with something industry standard. But yeah, it's going on. Right now, not included in the package.
Okay, there's another question from online. This is Andre Winkleman from Wolfson. Will this not all change again with proper SV 2012 support, which includes real number constraints and coverage? So did you get that question?
There was an echo on the line. Can you just...
Okay,
there was an echo, so can you just repeat the question?
Yeah, I'll repeat the question again. It's from Andre Winkleman, who's from Wolfson. Will this not all change again with proper System Verilog 2012 support, which includes real number constraint and coverage?
No, it'll not get changed, but it'll get enhanced, is what I can say. So the thing is, the constraint part of the code, right, doesn't lie inside the package. Constraint is something which user writes in his own test bench. So unless and until he complies to SV at that point in time being supported by the tool, it will work perfectly fine. So there is nothing which is going to break. It will always be backward compatible.
Another question from an online panelist, from Venkatesh. The question here is this all open source, or is it Synopsys specific? Right.
So again, as I talked about earlier, this is a package on top of the UVM, which is freely downloadable from the Accelera site. So the UVM-AMS package is part of Synopsys. I mean, we deliver it to the customer. but it is based out of UVM package which is deliverable from Excel. So this is an application package on top of what is downloadable. And right now it is Synopsys specific, but it doesn't require any licensing or anything like that. We can always engage it with the source code.
Okay, I don't think there's any questions from Grenoble. So there's no more questions from Bristol, and I don't think there's any more online questions. So it just remains to say thank you to our three speakers. Ratu from ST Ericsson in Grenoble, Jagannath from TVS in Bristol, and Abhishek from Synopsys in Bangalore. So thank you very much for your interesting talks. A quick reminder that our next event is Verification Futures in the UK. That's on November the 15th in Windsor. It's a full-day event. There's a full-day event in Grenoble on November the 21st, or in Germany, Munich, on 22nd. Okay. So thank you very much, and look out for your email to get the presentations. Thank you.